You know, every single time you tap your phone screen, send a message, or stream a video, you're kicking off this wild chain reaction of microscopic electrical pulses, firing billions of times per second. It is quite literally engineered magic. But today, our goal is to completely demystify that magic for you. We're going to break down exactly how a computer works from the inside out in this explainer. We'll start with the absolute tiniest, most fundamental piece of raw data, and we'll zoom all the way out to the complex global networks and operating software that pretty much govern our modern digital lives. Okay, let's dive into this. To really understand the architecture of our everyday devices, we're using a pretty unique blueprint, a literal computer science exam. Yep, we're reverse engineering this 80-mark masterclass, specifically the May 2024 OCR GCSE Computer Systems paper and its official mark scheme. Instead of just treating it like a test to pass, we're going to decode the exact concepts that demonstrate a total mastery of modern computing fundamentals. Here's our roadmap for today. 1. Decoding data and binary. 2. Inside the CPU. 3. Storing our digital world. 4. Connecting through networks. And finally, 5. Software, systems, and licensing. Let's kick things off with Section 1, Decoding Data and Binary. So at the very root of all computing, everything begins with raw data. Our source document opens with this really fascinating translation exercise, converting standard decimary numbers into 8-bit binary. Because remember, binary is the machine's native tongue. It's a language made entirely of ones and zeros. When the computer processes the 8-bit binary string 111000000, it directly translates that into the number 240. A string like 011010001 becomes 105, and 000111110, that's exactly 30. It really highlights the sheer elegance of digital architecture. We're taking highly complex information and distilling it all the way down into incredibly simple on and off electrical states. Now, what's really interesting about this slide is the profound impact of just a few of these bits. The blueprint challenges us to find the maximum number of different colors you can represent with just a 7-bit color depth. The answer? 128. With a mere 7 bits, a computer can assign a completely unique binary sequence to 128 distinct colors. Just to put that into perspective, think about the smartphone or the monitor you're looking at right now. Modern displays often use 24-bit or even 32-bit color depth. That allows them to render not just 128 colors, but literally millions and millions of them. It just brilliantly shows the explosive exponential power of adding a few more ones and zeros to the mix. Moving right along to Section 2, Inside the CPU. Okay, so it's one thing to have all this raw data floating around, but we need something to actually process it, right? So how does a CPU actually handle instructions? I mean, how does a tiny little square of silicon take those static ones and zeros and turn them into the dynamic actions that run our apps? The answer is this relentless microscopic assembly line known as the fetch, decode, execute cycle. First up is the fetch stage, where data and instructions are pulled directly from the computer's memory. Second, we decode. The CPU splits those instructions into an opcode and an operand. Basically, it's figuring out what specific operation to perform and exactly what data to perform it on. Finally, we hit the execute stage. This is where the arithmetic logic unit, or ALU, actually fires off the logical or arithmetic calculations. And what is truly mind-boggling here is that this high-speed assembly line is repeating itself billions of times every single second just to keep your device running smoothly. Now, to pull off this logistical miracle, the CPU relies on these incredibly fast, tiny storage areas called registers. You can think of them like the essential roles in a highly organized factory. The program counter, the PC, acts as the dispatcher. It keeps track of the address for the very next instruction. The memory address register, or MAR, is the delivery address, holding the exact location where data needs to be fetched from. Then you have the memory data register, the MDR, which is the package itself, holding the actual data that just got fetched. And finally, the accumulator, the ACC, serves as the CPU's quick scratch pad to instantly store the results of those calculations. So the crucial point is, this translates to a very real-world application. When you're out buying a new laptop or building a custom rig, these are the exact specs that dictate your machine's performance. Clock speed tells you how many of those fetch, decode, execute cycles can happen per second. More speed, faster processing. Cache size gives you a larger pool of ultra-fast memory right there on the chip, so the processor isn't just sitting around waiting for data.
and the number of cores allows multiple instructions to be processed completely simultaneously. Upgrade these three factors, and you are directly engineering the end of that dreaded loading wheel of death.
Which brings us to Section 3, storing our digital world. We've explored the brain of the machine, but where does the body permanently keep all this stuff? Our blueprint explores this through a really relatable scenario: a musician trying to decide how to store a massive library of audio files. Traditional magnetic storage offers massive capacity at a much cheaper cost per gigabyte. It is the perfect economical vault for archiving decades of old, finished albums. But solid-state storage, like an SSD, it has absolutely zero moving parts, which makes it incredibly durable and portable. More importantly, it boasts lightning-fast access speeds. If that musician is on stage rendering a heavy track live in front of a massive audience, that instantaneous read speed is absolutely vital. But hey, not all computing happens on a traditional desktop. The source outlines the concept of embedded systems. These are control systems built inside larger devices with dedicated hardware designed for one highly specific purpose. Consider the Follow Me system in a modern smart car, the one that automatically maintains a safe distance from the car ahead of you. This is a high-stakes, instantaneous environment. You absolutely do not want your car's braking system waiting for a background operating system update to finish. Because it runs a single dedicated loop of code, it relies on hyper-optimized hardware and just a tiny fraction of the RAM your personal computer uses. All right, let's jump into Section 4, connecting through networks. So how do these brilliant, isolated machines actually start talking to one another? Well, before any communication happens, a device has to identify itself on the local network using a MAC address. Now, unlike your IP address, which changes depending on whether you're at home or sitting in a coffee shop, your MAC address is totally permanent. It's a 48-bit hexadecimal number burned directly into the physical silicon of your network card at the factory. The first half identifies the exact manufacturer, and the second half acts as a unique serial number for your specific piece of hardware. It is an unchanging digital fingerprint. Network architects use these addresses to build incredible systems, carefully weighing the physical connections required. And this brilliantly illustrates the high-stakes airport scenario presented in the blueprint. Imagine the sheer chaos if an airport's automated baggage routing system ran on spotty Wi-Fi. No way! For critical infrastructure, wired networks are absolutely essential. They offer fast, secure, reliable bandwidth that is completely immune to interference. However, the gate agents and the terminal staff, they need to move freely across the airport to help passengers. For them, wireless networks are paramount. You get device flexibility and staff mobility without the astronomical cost of running physical cables to every single corner of the building. Inside the administrative offices of that airport, the computers and printers are often arranged in what's called a star topology. Every single device connects back to one central piece of hardware called a switch. The switch acts like a super smart traffic cop, receiving data and directing it only to its intended destination. It makes the network highly efficient and wonderfully easy to scale. But this brilliant design introduces some intense dramatic tension: the single point of failure. It is a perfectly harmonious system right up until that central switch breaks down. If the switch dies, the entire office instantly goes dark. Let's wrap things up with Section 5, software, systems, and licensing. We've built the hardware and we've networked it all together. But without an operating system, all of that expensive silicon is basically just a paperweight. The OS is the ultimate middleman. It seamlessly handles memory management, secretly moving data in and out of your RAM so you can multitask. It handles peripheral management, making sure your mouse and keyboard talk to the CPU without you ever noticing. It provides file management for organizing your life into logical folders. And it wraps all of this staggering complexity into a nice user interface, giving you a clean, graphical way to interact with the machine. Working right alongside the OS is utility software, which maintains the physical health of the machine. A really key utility here is defragmentation. Imagine your hard drive is a massive library, but over time, the chapters of a single book have been scattered randomly across totally different floors. It would take the librarian forever to walk around and gather the whole story, right? Well, when files are saved and deleted, data gets physically fragmented, exactly like this. Defragmentation software is basically the librarian stepping in, moving all those split files so they sit perfectly consecutively on the disk. This vastly reduces the physical movement required by the drive's read head, and it makes your data access significantly faster. But building software brings up a massive philosophical and financial dilemma for developers, which is captured in a really fascinating 8-mark debate within our blueprint. When a developer finishes a project, how do they actually license it? Do they choose open source, embracing a community ethos where the software is totally free and the source code can be openly viewed, altered, and redistributed? This invites global collaboration and super rapid bug fixing. Or do they choose proprietary software? Here, the code is heavily protected, users cannot alter it, and it's sold for profit. This allows the creator to fiercely protect their intellectual property and ensure they actually earn financial compensation for their grueling hard work. Let's move to and see how this builds into our final takeaway. As we step back and look at this complete blueprint, we have literally traced the very DNA of modern computing. We've journeyed from the elegant simplicity of 8-bit binary conversions, up through high-speed CPU cycles, varied storage mediums, vulnerable network topologies, all the way to complex software licensing. But digital architecture never stops evolving. So as we look at these foundations, we are left to wonder, as technology relentlessly races forward, what will be the next fundamental shift in how we build the anatomy of a machine? It's definitely something to think about the next time you tap that glass screen. Thank you so much for joining me on this explainer, and keep exploring.